This video will cover the basics of dense wavelength division multiplexing, or DWDM, including an overview of optical networks, multiplexing, WDM, DWDM components, and its advantages and disadvantages. An optical network increases capacity from 100G to over 10 terabits per second on a single fiber pair, without deploying more fiber. It also increases transmission distance from over 80 kilometers to thousands of kilometers without deploying lots of electronic equipment. We use infrared light for WDM wavelengths in an optical system. Optical fiber has loss, and the loss is different for different wavelengths, as shown in the graph. The wavelength applications of optical fibers are divided into several bands. The O band, 1260 to 1360 nanometers, has minimal signal distortion. The E band, 1360 to 1460 nanometers, is an extension of the O band. The S band, 1460 to 1530 nanometers, is the short wavelength band, which has lower fiber loss and is used by many passive optical network systems. The C band, 1530 to 1565 nanometers, is the conventional wavelength band. Optical fiber has the lowest loss in this band, making it ideal for long-distance transmission systems. The L band, 1565 to 1625 nanometers, is the second lowest loss wavelength band and is used when the C band is insufficient to meet bandwidth requirements. The ITUT band allocation shows the C and L bands. C-band products are commercially available for DWDM. Erbium-doped fiber amplifiers, or EDFA, are suitable for the C-band, with the flattest gain in the red band. Optical DWDM networking is important because it provides unlimited bandwidth on a fiber pair, offering bitrate and format protocol transparency, while also allowing for efficient use and rearrangement of embedded optical capacity, minimizing capital expenditure. The economics of WDM show savings in regeneration costs because a single optical amplifier can regenerate multiple channels. This drastically reduces the cost per channel and saves money compared to laying new fibers. It also allows for the introduction of a new network layer, reducing node costs. DWDM technology evolved from early WDM systems in the late 80s, which used two widely separated wavelengths. Subsequent generations increased channels and decreased spacing, leading to modern DWDM systems with up to 160 channels and 25 GHz spacing. Currently, the C-band from 1525 to 1565 nanometers is in use. Research is ongoing for the L-band from 1570 to 1620 nm and the S-band at 1400 nanometers. Multiplexing is the process of combining multiple analog or digital signals into one over a shared medium. Common types include time division multiplexing and frequency division multiplexing. Optically, we use time division multiplexing and wavelength division multiplexing. Wavelength division multiplexing, or WDM, uses different wavelengths, or colors, of laser light to multiplex optical carrier signals onto a single fiber. This technique also enables bidirectional communication over one strand of fiber. Key characteristics of WDM networks include transparency, allowing multiple protocols on the same fiber. Wavelength spacing, such as 50, 100, or 200 GHz, defines the number and selection of usable wavelengths. Wavelength capacity examples include 1.25 gigabits per second, 2.5 gigabits per second, and 10 gigabits per second. WDM overview. Multiple channels, each with an individual wavelength, are carried over the same fiber. Communication between devices, A with X and B with Y, occurs as if a dedicated fiber is used for each signal. WDM is now often referred to as coarse WDM, or CWDM, to distinguish it from DWDM. WDM is an attractive multiplexing technique, enabling a high aggregate bitrate without high-speed electronics. It is very useful for upgrading installed fibers and is realizable using commercial components. Potential issues include loss, crosstalk, and nonlinear effects. A simple DWDM system carries multiple information channels on one fiber, each using a unique wavelength. Unlike CWDM, DWDM channels are much closer. Each transmitter-receiver pair, T1 to R1, T2 to R2, and so on, operates as if connected by its own dedicated fiber. DWDM works by assigning each incoming signal to a specific wavelength in a tight spectral band, typically C or L band. A multiplexer combines them into a composite signal. The signal is amplified by EDFAs along the fiber. At the destination, a demultiplexer separates the individual wavelengths for the receivers. DWDM channel spacing is crucial for capacity. 40-channel DWDM commonly uses 100 GHz spacing, or about 0.8 nanometers. 80-channel systems use 50 GHz spacing. Ultra-dense 160-channel systems may use 25 GHz or even 12.5 GHz spacing. Typical passive DWDM components include gain equalization filters, Bragg gratings-based demultiplexers, array waveguide multiplexers/demultiplexers, and add/drop couplers. Active components and subsystems include transceivers, transponders, DFB lasers at ITU wavelengths, and DWDM flat erbium fiber amplifiers. The basic DWDM system components include transmitters, a DWDM multiplexer, optical amplifiers, a DWDM demultiplexer, and receivers connected by optical fiber. Optical network elements include transponders, optical amplifiers, optical demultiplexers, optical multiplexers, optical add-drop multiplexers, and optical cross-connects. In a DWDM system with add-drop capability, wavelengths can be added and dropped at intermediate locations using an add/drop-mux/demux. Each wavelength retains its own virtual fiber path. DWDM system spans define the distance between components. Optical amplifiers, including power, line, and receive preamps, extend the reach. Distances between amplifiers are around 160 to 200 kilometers, while the total system span can reach up to 600 to 700 kilometers or more with regeneration. For two-way communication, both ends of a fiber require transmitters and receivers. A transceiver combines a transmitter and receiver for a specific wavelength, allowing transmission in both directions. In classic DWDM systems, transceivers have electrical inputs and outputs. However, with SDH optical inputs and outputs, wavelength conversion is required. These converters are called transponders, changing the input wavelength to an ITU-specified C-band signal. A transponder or wavelength converter performs optical to electrical and electrical to optical conversion. It often includes electrical regeneration and is an essential component in optical networks. Transponders convert broadband optical signals to a specific DWDM wavelength using OEO conversion, also performing 2R or 3R regeneration. They are necessary when optical line termination equipment lacks tight tolerance ITU optics. Optical amplifiers offer several advantages, including design simplicity, high reliability, and low noise levels. They can amplify multiple wavelength signals within the operating band and prevent inter-channel interference. Careful design can also mitigate dispersion problems. EDFA amplifier, or erbium-doped fiber amplifier characteristics. Highly efficient, high gain, low noise figure, low cost. The EDFA is a simple device consisting of four main parts: the erbium-doped fiber, an optical pump, a coupler, and an isolator to cut off back-propagating noise. The diagram shows the typical setup. Conventional transmission, also known as simplex transmission, uses one fiber per direction. Linking two locations, therefore, involves two fibers and two transceivers, as shown in this diagram. Significant savings are possible with bidirectional transmission using WDM, called full duplex transmission. This method uses individual wavelengths for each direction and requires only one fiber, two WDM mux-demuxes, and two transceivers to link two locations. In bidirectional DWDM, different wavelength bands are used for transmission in each direction. These are typically the red band, the upper half of the C band to 1560 nanometers, and the blue band, the lower half of the C band from 1528 nanometers. To avoid interference, the red and blue bands must be separated by a guard band, typically about 5 nanometers wide. A disadvantage of bidirectional DWDM is that the guard band wastes spectral space. In DWDM, the aggregate optical power on a single fiber is high, leading to nonlinear effects and crosstalk. Common nonlinear effects include four-wave mixing, or FWM, and stimulated Raman scattering, or SRS. These effects depend on optical power levels and channel spacing. Coarse wavelength division multiplexing, or CWDM, uses wider channel spacing, typically 20 nanometers, and is more cost-effective than DWDM. CWDM is mainly deployed on single-mode fibers meeting ITU Rec. G.652 and in metro networks. CWDM is more cost-effective because it allows for less expensive uncooled lasers with less precise wavelength control due to wide channel spacing. Passive components like multiplexers are also lower cost, and CWDM components use less space on PCBs. A clear migration route from CWDM to DWDM is essential. This migration involves replacing the CWDM single-channel space with a DWDM band and is expected to occur with increased bandwidth demand and a reduction in DWDM costs. The advantages of DWDM include greater fiber capacity and easier network expansion. Expansion is simple. Just add a new wavelength with a low incremental cost for the new channel. There is no need to replace components like optical amplifiers. Limitations of DWDM include a maximum distance of 640 kilometers, made up of 8 80-kilometer spans. This assumes fiber attenuation of 0.28 decibels per kilometer and a span loss of 22 decibels. Total dispersion must be less than 12,800 picoseconds per nanometer. Disadvantages of DWDM are high initial and operational costs, complexity in design and implementation, and physical limitations of the fiber. It also has higher power and space requirements, maintenance challenges, and limited scalability for short distances. Thank you for watching. Please subscribe for more videos.